Now we're talking symmetry. So remember, there's three different types of symmetry. We could have y-axis symmetry, which basically just means we could fold it across the y-axis. And it means that for an x, if we have xy over here, that we have negative x, y over there, right? So this x and this negative x give out the same value. So this is like x squared, right? Like if I put in 2, I get out 4. If I put in negative 2, I also get out 4. So that would be a y-axis symmetry. X-axis symmetry is where it's reflected across the x-axis. And this is where we have the same x value, but opposite y values. So this would be like y squared, right? Because if I have 4 for x, it could be y squared could be 2, or it could be negative 2. And then we have origin symmetry, which is reflected across the line y equals x, which is basically through the origin, if you want to think of it that way. And so basically the idea is if I have x, y, then I would have negative x, negative y, right? Like I come down here to negative x, and then I reflect across to negative y. So there's obviously graphs can be symmetric against like all different other kinds of lines and points. They're a lot harder to see than these ones are, and we're not really going to focus on those. But we are going to test for these types of symmetry. There's a formal test for symmetry. Basically, so if we're looking for y-axis symmetry, right, reflection across the y-axis, we would just take x in the function and then we would replace it with negative x and see if it comes out the same. It should, right? So if I have like x squared and I replace that with negative x, if I had y equals x squared and I replace that with y equals negative x squared, what am I going to end up with? Negative x squared is still just x squared. So y equals x squared. So see how I get the same thing when I put in negative x, I get out the same value, or I get out the same function. Then that means that I have y-axis symmetry. It's symmetric about the y-axis. Or later we'll talk about the fact that it's even, right? We know that that's called an even function. X-axis symmetry, we replace y with negative y and see if we get the same thing. So this is like y squared equals x, right? If I put in negative y squared, then I would still end up with, right, because negative times a negative is a positive, I would still end up with y squared equals x. And since these two are equivalent, I know that that is symmetric about the x-axis. Then origin symmetry is if I replace x with negative x, I get out negative y. So I get the opposite out. If I put in the opposite, I get out the opposite. Okay, so this would be like y equals x cubed. Now let's see, if I put in y equals negative x cubed, what happens? Well, when I cubed negative 1, right, which is what is in front of that x, I get out negative 1, right? So when I simplify this, I get y equals negative x cubed. So I get out the opposite, replacing negative x with that, I get out the opposite, and then I need to replace y with negative y. So if I replace this y with negative y, I get negative y equals negative x cubed. And then I divide both sides by negative 1, I end up with y equals x cubed, right? And since this one is equivalent to this one, I replaced x with negative x and y with negative y, and I got out the same function. That means that this has origin symmetry. So that's kind of like the exhaustive proof that we would use in like higher level math classes. But we can also do the informal proof, which is what we did before, where we just basically say, let's pick a number. We're going to substitute it in. So if I pick 1, I'm going to also substitute in negative 1. And I'm going to see what comes out, okay? If I get the same number, then it's even, or I have y-axis symmetry. If I get opposite numbers, then I have origin symmetry. If I get totally different numbers, I don't have symmetry at all. And then the odd one out is this x-axis symmetry, because for x-axis symmetry, I have to do y values, right? Because basically what it's saying is if I have the same, if I have y, say y is 1 and y is negative 1, then I should get out the exact same x values. And if I do, then it has x-axis symmetry. Okay, so let's practice a few. First, let's figure out what type of symmetry this has. Let's do our informal proof first, and then we'll do the formal one. Okay, to verify, because sometimes the informal proof doesn't work, because sometimes you pick a number that makes you think you have symmetry when you really don't, right? So you pick 1 and it happens to come out perfect, but then you pick 2 and it doesn't come out perfect. So it has to come out perfect for every single number or it doesn't have symmetry. The other thing is if you come out with a 0, so if I put a number in and I end up with 0, then I need to pick another number, because 0 isn't negative or positive, so I can't really, use that as a proof. Okay, so we're going to pick 1 and -1. Oh, I just got a mosquito on my cheek. Gross. Right there. Okay. Anyway, this is what happens. I just wanted some fresh air, so I got the door open, and anyway, sorry. Back to calculus. All right, so we're going to do -1 and 1, and we're going to see what happens. If we get the same number, then we have an even function with y-axis symmetry. If we get opposite numbers, we have origin symmetry and an odd function. Okay, so let's see what happens. When I put in when I put in 1, I get y equals 2 minus 1, which says y equals 1. Okay, so when I put in 1, I get out 1. Now let's put in -1. Y equals 2 times -1 plus 1. So I get -2 plus 1, which is -1. So when I put in -1, I get out -1. Okay, so what did this tell me? I didn't get the same number, so it's not even and it doesn't have y-axis symmetry. I got the opposite number, which means I have origin symmetry. Okay, so this one has origin symmetry. We could do the mathy exhaustive proof here. Now that we believe it has origin symmetry, let's just check. Oop, I should have gotten my eraser, not the pen there. Okay, so what I have to do the proof is I say y equals 2. I replace x with -x. Okay, and then I replace y with -y. Because I believe it has origin symmetry, so let's just check to see if this comes out every single time. This means for any x, any y, or for any x, this would work, right? So I get -y equals -2x cubed plus x. And then I need to divide both sides by -1, and I get y equals 2x cubed minus x. Is that the same as that? Yes, it is. So our actual math formal proof says, yes, since I replaced x with -x and y with -y, and I got the same thing out, then this does in fact have origin symmetry. Okay, let's just do our informal proof on these ones. We can do the formal proof anytime you're questioning whether maybe like the number you picked just happened to work very nicely, but it doesn't actually have symmetry. I would do that. Okay, so we're going to just, again, do 1 and -1, and let's see what we get out. So when I put in 1, actually, let me do this in a different color so it's a little bit easier for you to keep track of. Okay, so when I put in 1, I get y equals the absolute value of 1 minus 2. So y equals 1 minus 2, so y equals -1. So when I put in 1, I get out -1. Now when I put in -1, I get y equals the absolute value of -1 minus 2. Y equals 1 minus 2, y equals -1. Okay, so I get out -1. So I put in opposites and got out the same number. This tells me it's even, or it has y-axis symmetry. This is even, or y-axis symmetry, okay? Finally, let's look at this one. Now, this one, I automatically look at it and say something's going on with y, right? Normally y is by itself. If y is by itself, then we're going to try the x ones first. We're going to replace x with -x. But I see y has the absolute value, so I'm assuming that this is probably going to have x-axis symmetry. This is actually going to be reflected across the x-axis. So let's just try that. If I have 1 and -1 as my y values, what do I get out for x? So that would be absolute value of 1 equals x minus 2. So this is 1 plus 2, so x equals 3. And then if I do this, absolute value of -1 equals x minus 2. So that's 1 plus 2. So x equals 3. Okay, so I put in 1 and -1 for y. I get out the same value. So this one has x-axis symmetry. And this one isn't called even or odd because it's not a function. Because it has to be a function to be even or odd. And remember, this one wouldn't be a function because it would be like a sideways V is what this one would look like. So just remember that even functions mean they have y-axis symmetry. And so even functions, if you remember, look like this or like this. I can't get it in the frame. You know what I mean. So they go all the way, both of them up or both of them down at the same time. Odd functions have origin symmetry, which means they go like this or they go like this, right? So one's up, one's down every time, right? And it's pretty easy to think about even and odd because even functions look like x squared, and we all know that x squared is a parabola, right? And then odd functions look like a line, right, where they go one and the other, or they look like x cubed, where it's like, remember, it comes down and it's got this loop loop, and then it keeps going. So really, even and odd shouldn't be too hard to remember. So we got to figure out if these are even, odd, or neither. So basically, we just do that same proof. We don't need to do the proof with the y. You know, we don't have to look for x-axis symmetry on these ones. We're just looking to figure out if they're even or odd. So we just check. We put in 1 and -1, and we see what comes out. So for this one, we get 1 minus 1 equals 0. Uh-oh. There's a problem because we got out 0. So that doesn't really tell us anything, right? So let's just change these to 2. Whoops. 2 and -2. Let's see what happens. Okay, 2 cubed is 8. Minus 2 is 6. And then -2 cubed is -8. Plus 2 is -6. So I put in opposites and I got out opposites. That means this one is odd. This is an odd function. It has origin symmetry. Okay. This one, again, let's just try 1. I always try 1 because it's so much easier to work with. And -1. And again, we could do those exhaustive math proofs, but we don't have to. So this is 1 minus 4, which is -3. And then this is 1 minus 4, which is -3. So I put in opposites and I got out the same number. That makes this one even. Okay, so again, this one's going to look like this or like this. Okay, and the first one is going to look like this or like this. Okay, last but not least, let's take a look at this one. We're going to put in 1 and -1 and see what happens. Okay, so we have 1 plus 2 plus 2, so that's 5. And then over here we have 1 minus 2 plus 2, which is 1. So see how I got out totally different numbers? That means this one is neither. This one is not symmetrical at all. And is not even or odd. So we could look at end behavior. You know, we could still figure out end behavior from this. We know that it's got an even degree, so we understand it's end behavior, but it's not an even function, meaning it doesn't reflect across the y-axis.